Watch the platform fall, and the first thing your eye wants to blame is the giant steel hanging above the dish. Arecibo's receiver platform drops into a 305-meter reflector, and the telescope that once defined radio astronomy ends in a few violent seconds. But the National Academy's report points to a stranger failure path. The decisive weakness was not a dramatic cable snapping in open air. It was a cable socket assembly losing its grip inside zinc-filled sockets after years of movement that the system did not treat as a hard stop. That is why this collapse is more unsettling than a simple old structure story. Repair planning had already begun. A controlled decommissioning decision had already been announced. The problem was that the support system was still redistributing load while people were trying to decide what could be done safely. The dates matter because they compress the trap. August produced the first pullout failure, November produced a main cable failure, November 19th produced the decommissioning announcement, and December 1st produced the fall. To understand that fall, we have to freeze the video before impact and ask a smaller question: what was really holding that platform up? Arecibo was built around one enormous bet. Instead of steering a full dish like a normal radio telescope, place a fixed 305-meter reflector into the Puerto Rican landscape and hang the active equipment above it. Completed in 1963, it remained the world's largest single-aperture radio telescope until 2016. It was not just famous because it was huge. The National Academy's report ties it to major discoveries, including work on binary pulsars and exoplanets, and NSF's own media materials still identify the site through its collapsed 2020 telescope and aftermath. The key object in this story is the suspended platform nearly 500 feet above the dish. After the 1997 upgrade added a Gregorian dome, 12 auxiliary cables were added to the support system, and the suspended platform weighed about 913 tons. That is the image to keep in your head: a science machine, the size of a landmark, with its most important working hardware hanging in the air from 3 towers. The collapse was not one object falling, it was an entire load path giving up. The comforting version of this story says, big cables have big safety margins. If the cable is strong enough, the platform stays up. If the cable is overloaded, it breaks. That simple picture is exactly why Arecibo is such a useful systems failure case. The upgraded cable system had safety factors greater than 2, which sounds like the kind of reserve that should keep panic far away. But those safety factors were mainly about cable strength, and the failure that mattered was not normal cable tensile failure. Each cable ended in a spelter socket, a connection where wire strands are held in place by zinc inside a socket body. The cable socket assembly was not expected to fail before the cable itself. The National Academy's committee also reported no design, material, or workmanship defect that materially contributed to the collapse. So the easy explanations do not carry the story. This was not just bad steel, bad math, or one careless build. The trap was that a conventional strength check could look reassuring while the connection that held the cable was aging in a different way. That distinction changes the whole maintenance problem. If you ask only whether the cable can carry the load, you can miss whether the socket is still transferring that load cleanly. Here is the mechanism that makes the whole collapse feel almost unfair. In a zinc-filled spelter socket, the cable wires spread into the socket, and the zinc is supposed to lock those wires in place so the cable can transfer load into the tower. The report found that, over the long term, zinc creep inside these sockets let the cable pull out. Creep is slow deformation under sustained load. In plain language, the socket did not have to explode, and the cable did not have to be loaded past its normal strength for the grip to get worse. The connection could slowly lose holding power. The National Academies described Arecibo as the first documented case of long-term zinc-induced creep failure, even though zinc spelter sockets had been used for more than a century. That is the frightening part. The system was not facing a known routine failure with a clear maintenance trigger. It was facing an unusual connector-level failure hidden inside the hardware that everyone expected to be stronger than the cable. And because the weak action was pull-out, the evidence could look boring until it was too late. A measured change at the socket, not a dramatic fracture across the cable span. The giant visible cables were only half the story. The invisible grip at their ends was the other half. The collapse sequence, according to the report, did not start on December 1, 2020. It began after Hurricane Maria, when inspections showed large and progressive cable pullouts. That matters because pullout is the visible clue for an invisible socket problem. One connection, socket M4NT, later became the site of the first cable failure. By 2019, it had documented pullout of 1.125 inches. The report notes that this was at least 1/3 of the cable diameter. That is not a tiny measurement lost in noise. It is the kind of movement that should force the question. If the cable is pulling through the socket, what is the socket still able to hold? It also should force a second question: how much more movement is allowed before the cable is no longer trusted? But the record did not show a replacement trigger tied to that condition. The telescope still stood, the platform still hung above the dish, and the support system still looked like a set of giant cables doing their job. The warning was not cinematic, it was a measurement, and in a big system, a measurement only saves you if the organization treats it as a decision. This is where the failure changes from a material problem into a systems problem. The committee found dramatic pullout at multiple connections, but no additional concern or action was documented. Staff and contracted structural engineers did not recognize cable pullout as growing socket distress in a way that forced remedial action. That wording matters. It is not the same as saying nobody saw anything. The problem was that what they saw did not become an urgent structural integrity gate. Safety factor thinking made the cables look strong, but the dangerous condition was happening at the sockets. Inspection could record movement, yet still failed to convert that movement into a pass or fail repair rule. For years, the platform was still hanging, which made the risk easier to normalize. Then the hidden failure stopped being a measurement and became a load path event. Once one cable actually came out, the remaining support system did not get to stay the same. It had to carry what the failed connection no longer carried. On August 10, 2020, the first major failure arrived. An auxiliary cable on Tower 4, identified in the outline as M4NT, pulled out of its socket, hit the Gregorian dome, and crashed onto the dish. That first break is important because it was not just damage to a famous telescope, it changed the math for every remaining Tower 4 cable. The National Academy's report says Tower 4 main cable loads increased after the first failure. In other words, the structure was no longer a quiet aging system with suspicious measurements. It was an active redistribution problem. One support had stopped sharing the load, so the surviving supports had to share more. And the report's conclusion that no design, material, or workmanship defect materially contributed to the collapse makes that redistribution even more uncomfortable. The system was not waiting for one bad cable to be swapped out, it was exposing a common weakness at a connection type that had not been expected to fail first. The first cable failure did not end the story, it made the next failure more likely to matter. For a short window, the story still looks like it might become a rescue operation. Then November closes that window. On November 6, 2020, a main Tower 4 cable failed at a zinc-filled socket. The outline notes the timing. Interim repairs were set to begin on November 9th, and repair material was already being staged. That is the brutal turn. The system did not fail after everyone ignored it forever. It failed again right as people were trying to move toward intervention. After this second failure, the remaining M4 cables carried still higher loads. The report gives the number that changes the mood. After the second failure, the remaining M4 cables rose to 800 kips. A structure that had once looked protected by reserve capacity was now concentrating more and more demand into fewer connections. On November 19th, NSF announced controlled decommissioning because safe repair was no longer possible. That decision is often heard as the end of the danger, but it was really an admission that the danger had outrun normal repair. Decommissioning is not magic, it is a plan, and plans take time. A damaged support system does not pause while the safest plan is being assembled. That brings us back to the video. On December 1, 2020, the remaining Tower 4 support system gave way. The report describes the final sequence as another socket failure. M42 failed, leaving the two remaining M4 cables overloaded above nominal strength. At that point, the load path had run out of places to go. The roughly 913-ton suspended platform collapsed into the 305-meter dish. In the real collapse footage, the fall feels sudden because the visible event happens in seconds, but mechanically it is the last frame of a longer chain. Post-Maria pullout, missed distress recognition, August auxiliary cable failure, November main cable failure, overload on the survivors, and finally the platform dropping through the reflector. The aftermath images show the dish torn open and the suspended instrument platform gone from the sky above it. The giant telescope did not simply die of old age. It failed because a hidden connection problem turned visible warnings into load redistribution, and load redistribution left the remaining supports with no safe reserve. The loss mattered because Arecibo was not a decorative landmark that happened to be old. It was a rare science capability. The National Academy's report emphasizes its history as a major radio and radar telescope, and NASA's statement on the planned decommissioning said Arecibo's planetary radar was one of two major planetary radar capabilities used to characterize known near-Earth objects. NASA also made the narrower caveat that near-Earth object discovery searches were not affected because radar characterizes objects that are already known rather than discovering them in the first place. That distinction is important. This was not the end of asteroid discovery, but it was the loss of a powerful way to study known objects in detail. It was also the end of Arecibo in its original 305-meter form, after decades in which the same facility had carried both scientific prestige and practical radar work. So the engineering failure was not only a structural case study, it removed capacity from science, from planetary radar work, and from the institution built around one of the most recognizable instruments on Earth. After the collapse, NSF's public materials describe cleanup, salvage remaining instruments, and later plans centered on an education and research center rather than rebuilding the 305-meter telescope. That afterlife is quieter than the collapse video, but it is where the lesson lands. Arecibo does not teach a lazy rule like inspect more, it teaches a sharper rule. When a unique aging system shows an unusual symptom, the symptom has to become a decision trigger before the load path starts failing. Traditional safety factors were not enough because they were looking at the cable as if cable strength was the main danger. The active danger was zinc creep inside connections. The committee's first documented finding makes the lesson even harder. Rare failure modes will not always arrive with a familiar checklist attached. The story begins with a platform falling from nearly 500 feet above a dish, but the real beginning is smaller. A cable slowly pulling through a socket, that is the system's warning. The part you can easily see may look massive, redundant, and safe. The part carrying the whole promise may be the piece you barely notice until it lets go.